Today we are going to cover the last section in Chapter 2, which is the chain rule. So finally we can look at the one in 2.4 and approach it in a little bit easier, have an easier approach to it than we did by foiling out x to the 9th plus 3x squared plus 10x to the third power. You guys remember that one on Wiley? Something like that. So 2.6, this is known as the chain rule. So we're going to calculate the derivative of a composition. In terms of the derivative, or the derivatives of the individual functions f and g. So the first theorem in this section is the chain rule. And it turns out if I have a function y equals f of g of x, I can let u equal g of x, so then I have y equals f of u. So dy over dx equals dy du times du dx. So y becomes a function of u. If I differentiate that function of u, I'm going to then multiply the function of u, the derivative of that, with respect to x. So let's look at the example that's from Wiley, I think 2.4. If I have f of x equals x to the 9th plus, we'll say 3x to the 6th plus x squared cubed, something like that. So what I can do here is I can let the inside function be u, and then I have a function just u to the third power, which I can differentiate really easy. So if I let u equal x to the 9th plus 3x to the 6th plus x squared, that means f of u becomes u cubed. So is everyone okay with that? I call my inside function u, so then I can just, my outside function is u cubed. So if I want to find, we'll call this y, so if I want to find dy dx, I take the derivative of y with respect to u. So this is y in function of u, and what's the derivative with respect to u? Very good, 3u squared. And I multiply that, the derivative of u with respect to x. What's the derivative of u with respect to x? Plus 2x. So now I want to write everything in terms of x. So I have the plug from here. I rewrite u in terms of x. So I can write this as 3 times x to the 9th plus 3x to the 6th plus x squared times 9x to the 8th plus 18x to the 5th plus 2x.
What about is squared?
This is squared, thank you. The u is squared, thank you. This is the way the book presents it with the chain rule, is I can always rewrite it. However, it gets a little cumbersome if I have a chain rule within a chain rule within a chain rule. If I have like 5 functions to write out each one of those functions and have u, w, p, s, whatever you want to name them, it gets kind of annoying. So there's another notation that is probably more commonly used, and that is if I'm taking the derivative of a composition, I take the derivative of the outside, evaluate it at the inside, so that means kind of hold the inside, times the derivative of the inside. So it's the derivative of the outside evaluated at the inside times the derivative of the inside. So if I look at this same example, do you guys see that the outside function is something cubed? So the derivative of the outside would be 3, that something, you leave alone, squared. You guys see that? So if I have something cubed and I take the derivative of it, is 3, that something squared, times the derivative of that something. So now I'm taking the derivative of the inside, which would be 9 x to the 8th plus 18 x to the 5th plus 2x. So basically I just got the derivative by doing it in our head by starting on the outside, evaluating the inside times the derivative of the inside. I didn't specifically have to write out the two relationships.
Can you simplify that more?
Go ahead.
So when you did the derivative of the outside, basically you're treating the whole parentheses as the x,
Yes.
and then the 3's the a. You brought it down.
Yes.
Okay.
You don't have to simplify this more. This is perfectly fine. However, be very careful with your parentheses. They are very important. If you lose parentheses here, it's a totally different relationship. It would be wrong. So it's the derivative of the outside evaluated at the inside. So you take the derivative of the outside, hold the inside, times the derivative of the inside. So that might be kind of useful to write out. So the derivative of a composition is the derivative of the inside, sorry, the outside, the derivative of the outside, evaluated, outside function, evaluated at the inside, times the derivative of the inside function. So I have the derivative of the outside, hold the inside, times the derivative of the inside. So let's look at another example. Let's say W is tangent of 4x cubed plus t. So can you guys clearly see the two functions here? The outside function is tangent and the inside function is t x cubed plus t. So if I was to find the derivative of w with respect to t, what is the derivative of tangent?
Secant squared.
Secant squared. The derivative of tangent x would be secant squared x. But the derivative of tangent tangent of 4x cubed plus t would be secant squared 4x cubed plus t. Derivative of the outside evaluated at the inside. Times, what's the derivative of the inside? Great. Generally, we write polynomials in front of the trig functions, so I might rewrite this. This is clear that this is being multiplied, and if you write it like this, you won't lose points. This is just aesthetically a little nicer on the eyes. Any questions on that? see what else we have. Let's try h of x, cosine of x cubed. So what's h prime of x? Very good. So I have negative sine x cubed. Perfect. Times 3x squared. Generally, we would like to write this as minus 3x squared sine of x cubed. If I was to take the second derivative, I'd have to use a product rule within a chain rule. Or the chain rule within a product rule, right? Let's go ahead and take the second derivative. What would be h double prime?
So you just do the same process.
I do the same process. I take the derivative of the first function. Since I have a function times a function here, I take the derivative of the first function, hold the second one, plus the derivative of the second one, hold the first. Right, so let me just write this out. I'm going to take the derivative with respect to x of minus 3x squared, hold the second function, plus the derivative of the second function hold the first function. So what's the derivative of minus 3x squared? Minus 6x times sine of x cubed. Plus, what's the derivative of sine of x cubed? Very good. So cleaning it up a little bit, I have minus 6x sine of x cubed minus 9x to the fourth cosine of x cubed.
Excuse me. And the cosine, we roll like 3 x cubed cos x cubed.
This cosine of x cubed?
Yeah.
Yeah.
And they round out 3x squared.
Where does this 3x squared come from? It's the derivative of the inside. A lot of people forget to take the derivative of the inside when they do, problems like this. If it was cosine of x squared, if this was sine of x squared, it would be sine of x squared. This was sine of x squared. This would be cosine of x squared times 2x. You have to take the derivative of the inside.
Well, if we are like taking the derivative of sine s cubed, we also do it in the chain rule form.
Yes, because you have a function within a function here. And then that's the derivative of the first function and then holding the second one.
Is that a subtraction sign between the two?
This?
Yeah.
Yes. You see why it's negative? Because I have negative 3 times 3. So I could end up taking the third derivative, which I would have to use the product rule here, and the product rule here, and the chain rule here, and the chain rule here. And I could keep going, right? So now we know the derivative of polynomials, the derivative of trig functions, the derivative of the sum of functions, the difference of functions, the multiplication of functions, the division of functions, which I think I already said. And now we know the composition of functions. So if I have a function within a function, that's a composition, I can find the derivative by using the chain rule. Derivative of the outside, evaluated the inside, times the derivative of the inside. Question?
Okay, when you have the derivative of sine x cubed, on the other sheet, you just the derivative of sine and the derivative of inside. So what was the difference? Like, how come on that one take the derivative of inside too?
Here?
Further down, the one that gentleman was talking about. So,
This one? Yeah, so what's the derivative of sine x cubed?
well, my only point is
Yeah.
before on the other sheet of paper you did just the derivative of sine and then the derivative of what was in parentheses.
on today's lecture? So this is the only time I've talked about derivative of sine and cosine in this little area.
It might have been that.
Okay, so here I took the derivative of this function, cosine of x cubed, which would be minus sine.
And you still keep the inside and then do whatever.
Yes.
derivative.
Yes, and that's what I did here, right? The derivative of sine would be cosine. I kept the inside, but then I took the derivative of the inside. Does that clarify anything, or?
Yeah.
Okay.
Is there a list of general equations for each rule in our book? So that
There
you don't
is.
have to do them inside of each other, you don't get too confused?
There is a list on, or a table, I think. I think there's a table, but let's just look at, okay, some review. So we know that the derivative with respect to x of a constant is 0. The derivative with respect to x of x to the n would be n x to the n minus 1. We know the derivative with respect to x of sine is cosine. We know the derivative with respect to x of cosine is minus sine. Those are the only ones we definitely have to memorize. The other 4 we can derive, but let's go ahead and write them. So what's the derivative of tangent? Secant squared. What's the derivative of cosecant?
Negative cosecant cosine.
And the derivative of secant?
Secant times the tangent.
Very good. Secant times tangent. And the derivative of cotangent?
Negative cosecant squared.
Very good. These 4, it's not the end of the world if you don't memorize them. It might save you 15 seconds on an exam if you have it memorized, but it doesn't take too long to write secant as 1 over cosine, and then take the derivative of the top, hold the bottom, minus the derivative of the bottom, hold the top over the bottom squared, and find out its secant tangent. It's not... Okay, so those are pretty much things we know. But let's say if we take the derivative with respect to x of f of x times g of x. That's the derivative of the first one, hold the second one, plus the derivative of the second one, hold the first one. So that's the product rule. What if I have a function divided by a function? So the derivative of the top, hold the bottom, minus the derivative of the bottom, hold the top over the bottom squared. And then today we just learned,
So it's product and quotient, right?
yes. The chain rule.
What's dy over dx again?
dy over dx would be, if I said something like y is f of x, then y prime would be written as dy over dx, which would be the same thing as d dx over f of x. So a lot of times when they say y is a function, they say find dy dx. Y is f of x, so you're really finding the derivative of this f of x with respect to x. Those are good questions. So you need to know these 3 formulas specifically and how to apply them when I have maybe a polynomial times a trig function within a overall polynomial type thing, some kind of composition. You guys remember all those? Going over them? So let's look at a couple more examples. Let's say we want to find the derivative with respect to x. So the derivative with respect to x of x squared minus x plus 2. to the 3/4. So what is the derivative of this function? What is the outside function? Something to the 3/4. So what would be the derivative of something to the 3/4? Yeah, very good. 3/4, that's something to the minus 1/4. So the outside function, I bring down the power, hold the inside function, times 3/4 minus 1, which would be minus 1/4. Times the derivative of the inside. And what's the derivative of the inside? Perfect. So I might write that as 3 times 2x minus 1 over 4, the square root of x squared minus x plus 2. But you wouldn't have to. This is correct as well. I can distribute the 3 in there. Not much else I could do.
I should get the square root. So what about
Oh, it's not the square root. It would be the 4th root. Sorry. Yeah. Or I could just write it to the 1/4 power in the denominator. Make sense? Let's see what else we have. Okay, so let's look at some problems from the book. And these will be similar to Wiley. So 2.6. So let's look at number 2. So number 2 states you're given f prime of 9 is 5. G at 2 is 9. And f prime at, G prime at 2 is minus 3. And they want you to find f of g prime at 2. So find the composition, find the derivative of the composition at 2. What do we get? What? It would be negative 15. Does anyone have any questions where that came from? Let me guess, 5 times minus 3? Okay, so this is how it works. I take the derivative of the outside function evaluated at the inside function. The inside function is evaluated at 2. Times the derivative of the inside evaluated at 2. G of 2 is 9. So really, I'm taking the derivative of f at 9 times g prime at 2, which we know is minus 3. So f prime at 9 is 5 times minus 3, which would be minus 15. So this is kind of where the evaluated at the inside. G of 2 is going to be what I put into f prime. I don't put in 2 of f prime. I put in g of 2.
So f prime of 9.
Times g prime at 2, but g prime at 2 is 3, minus 3.
I thought we were going to take the derivative of f prime 9.
We take the derivative of the outside function evaluated at the inside. And the inside is g. And g is evaluated at 2. So the derivative of the outside evaluated at the inside times the derivative of the inside. The derivative of the inside would be g prime at 2. But I plug in g of 2 for the outside function, the derivative of the outside function. G of 2 is 9. So I plug in 9 to f prime, which gives me 5. So this way, it's like, okay, I can clearly see you kind of understand the setup, because there's no function involved. I didn't tell you what the function is. Because if I did, you could just plug in 2 into the derivative of the function once you differentiated it. But here you have to know that you're plugging in g of 2 to the outside function. So your book also has you set up compositions. Let's look at number 4. It says, let f of x equal 5 square root of x and g of x equal 4 plus cosine of x. In part A, they ask you to find f of g of x.
No on the screen.
Oh, sorry. And also find f of g prime of x. Part B, they ask you to find g of f of x and g of f prime of x. So, composition, I take the outside function and I evaluate it at the inside. So in this example, the outside function is f. So really I have f of g of x. What this means is everywhere I have an x in my original function, my original outside function, I plug in the inside function completely. So what is going to be the composition f of g of x? Perfect. You guys see that? What about g of f of x? This would be g of f of x. 4 plus cosine. Perfect. So these are not commutative. Composition's not commutative. F of g is different than g of f. F of g is different than g of x. G of f. Question?
On that cosine,
Mhm.
does that mean cosine of 5 times the square root of it?
Does that help?
get
Yeah.
confused.
I know parentheses are important. So
So
yeah.
that's just a number when you're evaluating.
Yes.
Okay.
So basically, the x is a placeholder. So what I have f of g of x, that means everywhere I have the placeholder x in my original f function, I replace that with my g of x function. The same thing down here, except my outside function is this g function, g of x. So everywhere I have a variable in g of x, I replace it with the whole f of x function. So now let's look at what is the derivative of f of g of x.
When you write it like that, does that mean f prime of g prime of x, or does that mean f of g prime of x?
This means f of g of x prime. So you take the composition, you find the derivative. Yeah, so this would be, and that's the notation from your book. I'll show you there. So your book uses this notation, and that means this is a composition function, which is just another function. And then here it's saying you take the derivative of the composition you just found. So. Good. 5 over 2. Well, we're not done. So, times 4 plus cosine of x to the minus 1/2 times minus sine of x. So generally, I would pull out this negative out front so I don't get confused with it being times a negative versus subtracting a sine of x. So I'd write that potentially minus 5 sine of x over 2 the square root 4 plus cosine of x. So how I got this? This is the function I want to find the derivative of. So I leave 5 alone because it's a constant. And I take the derivative of this function. So this function is something to the 1/2 power. The derivative of something to the half power is 1/2 something to the minus 1/2, right? So I would have 1/2 something to the minus 1/2. I leave this alone. So then I take the derivative of this inside. And the derivative of the inside would be 0 minus sine of x. So I don't write this either. We have the derivative of cosine is minus sine.
So it's like you did the 5 and then you took the 4 plus cosine x to the 1/2 power.
Yes.
Okay.
So a lot of times I like to see things as powers instead of roots, but they're given to you in roots a lot of times. So you know, go ahead.
So the outside, so once you do that, then you see that the outside function really is the 5 and the 1/2, and that's what you put down.
The 5 is a constant. So the outside function is something to the 1/2. Something to the 1/2. So on chain rules, you always start on the outside, the furthest outside you can get, and you take the derivative of that, leave everything on the inside alone. Evaluate it on the inside. And then you just kind of work your way inward slowly until the derivative is 1. So here I take the outside function here would be something to the 1/2. And the derivative of something to the 1/2 is 1/2 something to the minus 1/2. But I evaluated at that something, that placeholder. Then I take the derivative of the inside. I may or may not need to do the chain rule multiple times. So the next example we'll do the chain rule more than once. So let's finish this one though. What is going to be the derivative of g of f of x? Close. So negative 5 sine of 5 square root of x. Good. Yeah. So really, so I got the negative 5 from taking the derivative of the inside, but I also have a 1/2 x the minus 1/2. Oh, it's not negative. Oh yeah, it is because the derivative of cosine is minus sine. So the 5 came from the derivative of the inside, but I also forgot the 1/2 x the minus 1/2. Question.
Could you like not write? Could you write the 5 as 5 halves x to the negative 1/2?
Definitely you would.
Okay.
Yeah, so simplifying this, I would write this as, potentially minus 5 over 2 x the minus 1/2 sine of 5 square root of x. But I could go one step further and write it as minus 5 sine square root of 5x over 2 square root of x.
So what's the outside function of that?
The outside function here is cosine, because the derivative of 4 is 0. So the outside function is cosine, the derivative of cosine is minus sine.
Where did the 5 come
The 5 came, so they jumped a little bit ahead of themselves, because they know the derivative of the inside is 5. But the derivative of the inside is actually 5 over 2x to the minus 1/2. So if I was writing this up, I would have probably written it as minus sine of 5 squared of x. Does everyone see where that comes from? Derivative of the outside evaluated the inside times the derivative of the inside, which would be 5 times 1/2 x to the minus 1/2. And the derivative of the inside function here would just be 1, because the derivative of x is 1. You guys see that? And then, of course, it can be written multiple different ways there. So I can pull out the minus 5 over 2, bring down the x to the minus 1/2.
How did 5 get in this group?
Here
Yeah. No.
or here?
She's talking
In
about the bottom
the
right
square
corner.
root. The bottom right.
This? How this 5 get in the square root? This 5's always been in the square root. This 5 on the outside?
It was 5 times square root of x.
To begin with, right? So if I differentiate this function, I have the derivative of the outside evaluated at the inside. So I always leave the inside alone, which was 5. Yeah, that's the problem. 5 squared of x. Yeah, this would have always been the 5 square root of 5x, right? Thank you. Makes sense? This should also be the square root of 5x. I don't know why. Sorry about that, guys. Yeah, you leave the inside completely alone. Take the derivative of the outside, leave the inside completely alone. Same thing here. Oh my goodness.
So then it wouldn't be 5 negative
it would be square root of 5. Wait, why did I put it under there in the beginning? It should have never been under there. Okay, okay, so I was right up until the very last point, and then I switched everything else. Okay, so let's just write this here. Minus sine.
Your g of x wrong.
Did I?
Yeah, because your g of x was, or f of x was,
5 square root of 5. That's what it would have been in the beginning.
yeah, 5 square root of x. So, yeah, I
So,
think.
yeah, I think I figured out what I did. I wrote it wrong right here.
Oh,
And then I thought I wrote it wrong in the previous 5 steps, but I didn't. I only wrote it wrong in my last, yeah, sorry. Yes. And now we're going to fix it. So all your guys' should be right up until the very last point, but now they're wrong because I messed them up, and now we're fixing them. So math is fun, right? Yeah, so I take negative sine, evaluate it at the inside, and the inside, leave it alone, right? Times the derivative of the inside, which would be 5 times 1/2 x to the minus 1/2. So we get minus 5 over 2 x to the minus 1/2 sine of 5 square root of x. Sorry about that, guys.
And you can write it the other way, like I said, but for whatever.
Yeah,
Like it that
preferably.
way. Yeah.
Yeah, because think about, okay, well, let's say we need to take the derivative again. If we wrote it the other way, we'd have to use the quotient rule. Which the quotient rule is fine and all, but the product rule is a lot easier than the quotient rule. So here, I would just do the product rule, and I already have it set up as x to a power, and things work out good if I need to do the derivative again. If I write it like this, and I need to do the derivative, it's like, okay, the derivative at the top, or the bottom, minus, they're equivalent, you'll get the same answer, it'll just look a little different.
So sine isn't negative?
Well, the negative's out front.
Okay, so that's what distribute.
Yeah, so generally we pull the negative out front, because then if I have a negative here, it looks like this minus this. So you have to be a little careful with that. So we pull that negative out front. Question?
So if you took the derivative again, it'd be negative 5 halves x and then negative 1/2, and that'd be one thing. And
You-
the sine.
You'd have to use the product rule. So you could say, okay, hold this function.
Okay, I didn't know which one was how you separated.
Yeah, so we have the last couple minutes, and let's say we have to take the derivative of this again. So let's say we are given a function y equals minus 5 over 2 x to the minus 1/2 sine of 5 square root of x. And I want to find the derivative of this function. So sometimes it's beneficial to write out what we're doing. I'm taking the derivative of the first function, holding the second function, plus the derivative of the second function holding the first function. And we can take the derivative of each one of these parts, right? So this is relatively, so this would be minus 5 over 2 times a minus 1/2 x to the minus 3 over 2. Hold the sine of 5 square root of x. Plus the derivative of sine of 5 square root of x would be cosine of 5 square root of x times 5 over 2x to the minus 1/2. So I have some cleaning up to do, but so if I had to take the derivative again, I'm going to have to use the product rule twice. So I'm going to have, I'll have 8 terms, right? I would have 2 terms for the derivative of this one, hold this one, plus derivative of this one, hold this one. So sorry, I'd have 4 terms, not 8, 4. I'd have 2 terms here and 2 terms when I take the derivative of this function.
Why would you want to find the setting of code?
So in physics, there's some applications. We know the first derivative of position is acceleration. The derivative of position is velocity. The derivative of velocity is acceleration. So I might say, when's the acceleration 0? And so you need to find circuits, electrical engineering. There's the derivative of voltage is current, and the derivative of current is flux. So the third derivative there has meaning as well. So you'll apply these and say, okay, when is the current maximum? At what point? Question.
So is physics way easier than calculus?
Calculus was invented to solve physics problems. So definitely so. Calculus makes physics sense. Makes physics make sense. Without calculus, you can't really do physics. All right. I will see you guys.